Hi everyone, this is me Abdullah Meman. My topic is data driven modeling and control strategy for DC motor performance enhancement for Simulink Student Challenge 2024. The motivation behind this research that usually model is modeled using mathematical modeling, but there can be errors in the numerical calculations, and to avoid those calculation mistakes, multiple data driven control strategies have been explored, and also it has been compared with each other, and ultimately at the end we are proposing a control strategy for the robust performance. Here our system is DC motor. We are simply using the DC motor for our to explore the system identification technique. These are our contribution. So the system broadly modeled in two ways: physics based modeling and the data driven modeling, and specifically it can be modeled by using a transfer function, state space differential equation and the algebraic equation, and by using the data it can be modeled using system identification toolbox and the Knox modeling. This is our complete project flowchart. We start our project by developing a simscape model of a DC motor. We run the model and get the data, and we use those data to identify a model by using system identification toolbox and training the Knox network. These both things have been used in the MATLAB. At the end we compare its responses. This is the fundamental DC motor model. Voltage source, resistor, inductor, motor, and it has been connected to some load. So this is the simscape model for the DC motor. Like, we are not using any mathematical equation for the DC motor. We are using the physical resistor, inductor, inertia, damper, sensor, and here our input is voltage, output is speed. Our aim is to control the speed by giving the input voltage, and from here we are taking the input voltage and output speed, and we are using it for additional application. And these are the values that have been selected for the physical simscape modeling of a DC motor. It has been taken from the literature to represent the actual DC motor. This is the input voltage and output speed that has been obtained from the simscape modeling. Actually, simscape model allows us to use the physical components for the electrical, mechanical, hydraulic. This is a good feature, and for simscape modeling we don't need to understand the mathematics or physics behind it to model the system. So we use this data for the system identification. There is a toolbox in the MATLAB system SI toolbox, and we got the transfer function, and it took five number of iterations, and the error we obtained, and the fit estimation rate is 96%. This transfer function is correct or wrong, we validated it by comparing it with the standard transfer function model. Here we have used the same value giving in the previous earlier table, and we got both the transfer function are approximately the same. Then transfer function is also modeled in the Simulink, and it has been compared with the DC motor model. Afterwards, we estimate the model by using a Knox technique, non-linear auto-executive exogenous input, that takes the current input and the previous output. It is also been used by using the Knox toolbox, and these are the parameters and values that have been taken. And afterwards, we compare the simscape model transfer function in the Knox model in the Simulink. Here we compare it, and for the Knox we tested different level of inputs like 1 1 2 2 3 3 4 4 and 5, and we got that the Knox 2 network is giving the better response, so we selected it for the further application. And here we got approximately the same response for the DC motor transfer function and the Knox network for this input voltage. And we designed the PID controller for our DC motor model. We designed and implemented on the DC motor, and the gains are tuned by using auto tuning application. We got these gains: PI, KP, KI, KD and KN. And for this reference voltage we got this response, this speed for the reference voltage, which is I think which is very good. Now we have implemented the genetic algorithm PID. This is the response before tuning, and after tuning it has also been modeled in the Simulink. Afterwards, we designed and implemented the genetic algorithm PID. This is the complete flow for the genetic algorithm PID, and this is a convergence graph, and this is for the specification that has been taken for the genetic algorithm, and these are the gains that have been obtained. And here we have used integral time absolute error as an objective function to calculate the gains. And this is the response. This is the comparison between the auto-tuned and the genetic algorithm PID, and it can be observed that genetic algorithm PID has greater and smooth response. It has been modeled here. We are modeling the integral time absolute error to calculate the gains. There are also tabulated results like comparison in terms of rise time, settling time, overshoot, and transient time. And it can be observed that the genetic ozone PID has least overshoot, has least rise time, has least settling time, and has least transient time. Thank you. This is the complete research.